So what is my idea today? This is not technical, no mathematica. I want to show you the overview, the big ideas of what is happening with this automated reasoning tools, and in particular my tools, TPTP. What is it? What can we do with it? How can we make money with it? So this is what. Then I'm going to be here all week. And tomorrow at 4 p.m. we will have a practical session to play with it together. We can sit. If you have a laptop, you can use it, or we all just talk. Practical session for people who want to learn. Then I'm here Wednesday, Mercury, see? Thursday, Friday. We can teach. I can show you anything what you want. Not what I want, what you want. You decide, I will teach. And then on Saturday, Miami. Okay, I'm going to sit because I like to use my computer sitting, but this is what I look like standing up, okay? And all of these slides are on the internet. Everything's on the internet, free. So you just take it if you want it. Here's what you do. If you go to your internet on your phone, this is your new page, tptp.org, huh? All right. And that, inside here, all my talks are here. All the software, all the data, everything is connected here. All right, so you don't need to worry about remembering anything. You can find it. And also, I can do it in Spanish. Thank you, Google. Right, but I do it in English. Okay, so the first question, what is this? ATP, Automatic Theorem Proving. In mathematics, you prove theorems with your pen and your paper, huh? And it's horrible. But now we use a computer to prove the theorems. And in mathematics, you have to say, here are my axioms. What do I know? Here is my theorem. This is what I want to prove. And you have to make a very careful proof. And so now I want to show how we can do that with a computer, so we don't need the mathematicians anymore. Okay, no, we keep them. So what is it? So I think about the world, el mundo. And there are many problems in the world, huh? We know there are problems you want to solve. There are problems in politics. There are problems in industry. There are problems in mathematics. There are problems in health. How do we solve world problems? Well, the main thing, what we'd really like to do is just say, find the problem and go straight to a solution. But this is often not possible because it's difficult to find a solution, huh? So, with these automatic tools, we take a different pathway. We take the world problem and we convert it to a logic problem, huh? Like a formal definition, describe the problem. We then take the logic problem and we give it to the computer program, the automated reasoning program. It produces a logic solution. Then we take the logic solution and convert back to a world solution. So that's another pathway. It's an interesting problem. So what we have to do for this is we have to describe the world problem. How do we describe it? So here we have the world, el mundo. We write down how to describe the world. Maybe it's the world of algebra. We're doing Boolean algebra. We write down the axioms of Boolean algebra. Maybe we're talking about a business. How do businesses grow and make money? We write down how businesses work in a formal way. And then the problem we write as a conjecture. So this is logic in black. It's logic. Then we can hand the description of the world, the description of the problem to the software. The software produces a logic answer, maybe if it's a proof, but there are other types of answer. And then we go to a world solution. So the green is the world problem. We go through this translation and we get a world solution. So that's how we have to do it. Now, if the world has a problem they cannot solve and we can solve it, then we can make money. And this is the game. Okay, we buy a boat, El Barco Grande. All right. So how do the tools work? So the normal way to describe this is we take the axioms, they describe the world. We take the conjecture, describes the problem. We give it to the software, and there's plenty of free software. and then we push go. All right? And what possible things does the software say? The software might say, yes, I have a solution, and you go, yes, good news. Or the software might say, no, there is no solution, and then you cry. All right. And often, because this is very complicated, very difficult, you say, I give you 3 minutes, and it says, I don't know, 3 minutes, I cannot help you. And you try 5 minutes or something. So that's the general idea. The software that we're using, and we can play with tomorrow, and I will show you today some software executing, has a standard mathematical way of doing a proof. It's the proof by contradiction. Everybody, I hope, is familiar with that from mathematics. We take the axioms and the not, the negation of the conjecture, and we show contradiction, proof by contradiction. Everybody, I think, should know that from beginning math. And so with this tool, we give it to the system. It says, yes, there is a contradiction, and we say, yay, we have a proof. Or it says, there is no contradiction, and we cry. Or it says, I don't know, 3 minutes, not enough. Now, people might understand we are looking for a contradiction. And so, what happens if there is a contradiction here? If your description of the world is bad, then you can prove anything. If you are sitting with your friend and you make your friend say a contradiction, then you have a proof. You owe me 10,000 mil. Okay, because you can prove anything. So we cannot have a contradiction in the axioms. We have to be sure the axioms are good. And so for that, we can take the axioms, and we have special software, special programs to check that the axioms are okay, they're consistent, they don't have a conflict. And it's the same software about similar ideas. It says, yes, axioms are good, no, we cry, and time out, don't know what to do. So now we're going to have a challenge, and everybody has to turn on your brain now, maximum brain power. Oh, but wait, there it is in English, but I have it good news. I'll put it in Spanish. For everybody here, it's easier. Okay, you have to read the problem, and we decide what is the answer. You have to think. I'll be quiet now. Now we'll see who gets the answer. I give you 2 more minutes. And don't ask ChatGPT. It cannot do it. It gets it wrong. I will show you today at the end of my talk. We will give this problem to ChatGPT, and the wrong person goes to jail. Quite difficult, huh? Not so easy. For a computer, it's very easy. Yeah, no one can work it out. Okay, who decides? So we take a vote, eh? What's vote in Spanish? Tell them, vote. Okay, so who says the butler? The butler. Mayordomo. Mayordomo. 1, 2, 3, 4, 5, 6, 7. Okay. Charles. Whoa! Yeah, Maximo. Okay, so Charles did it. Aha. But not so. Yeah. Yeah. And so now Charles, Police, Charles, off to jail because of you. Yeah, not so good. So, we have to describe the world carefully, describe the problem, and then give it to the computer program, and Charles goes happy, and Major Domo goes happy, Mayor Domo goes happy, and Butler, morte. So, next question. How do we make money with this software? So, the beginning of this software is from 1965, so 80 years now. And the beginning was for mathematics. Here we go, for Mathematica. And the very famous problem, you know this problem, Robin's problem? In algebra. You say every Robin's algebra is a Boolean algebra. And Tarski, you know Professor Tarski from a long time ago, him and his PhD students, they tried to make a proof. For 20 years, they could not make a proof. And then along came automatic theorem proving, and it was solved, and it proved it. So we proved that every Robin's algebra is a Boolean algebra. So that was good basic mathematics. We solved the problem in mathematics. There's lots of other use in mathematics, from the old days to modern mathematics. I know there's going to be the mathematics department in the University of Miami will have a conference next year. So there's Wu's method for geometry, to prove geometry problems. This work here is again in algebra. This is very present mathematics research. It's not old math, it's just new math happening. This is done work in Albuquerque. I don't know if people know the Mizar library. It's a big library of mathematical truth, and there's a journal. We've done that. Mathematica, do they use Mathematica? Anyone use Mathematica? Is software? Yeah. Okay. Inside Mathematica is one of these automated theorem prover. It's inside, it's one piece. When you do solve equation, it calls that. So that's the sort of history. Now, at the moment, where the big money is verification. Because if you have software on your phone, software on your computer, and it does bad things, then you are not happy. And so you can use automatic theorem proving to check the quality of software and to check the quality of hardware. Is the electronics good? Is the design good? Is your software, Java, Python, Rust, whatever, DDDD? If we can look for the bugs, we can find mistakes. This is work that was done at NASA. They're sending the rockets. Remember Hubble Space Telescope? The software for that, I worked on the verification, because when you send a rocket to space, no Control-Alt-Del, you can't reach, it's too high. So you have to check the software. Which one was this? Oh, this was a good one. Who programs in Java? Java, Java people? Yeah, Java? A few, not many. So in Java, there is a built-in sorting algorithm. You can do arrays sort, just to sort into ascending order. And it's called a bucket sort. And there was a mistake in the Java library until 5 years ago. You could make an array, random, not random, special one, tell it sort, and it would not sort it correctly. There was a mistake in the software. And this matters. I mean, this is critical. Sorting is a basic software. And we found that this was people in Denmark, I think, who did that. Other people who work on this, Microsoft, Redmond, big research group, testing a lot of things. When you're in Microsoft, you have a device driver to talk to your internet and your Wi-Fi and your hard disk. How do you check the software? Microsoft have a big team. One I wanted to mention, it's not here, Amazon. So Amazon do this. They have a big team of people who use this software to check Amazon Web Services. When you buy some Amazon Web Service, they check what you want for you. And they check that you're asking for something good. Intel do it to make sure their computer chips are good, ARM or the companies. So there are companies that these people making big money at the moment. I mean, and there's good work available. We all know about security on the internet. And we can check the security when you use SSH or HTTPS. So you have secure internet. We can check all of that. All right. But then we get some more fun stuff. This is where it's kind of nice. So there's a TV show, I don't know if it's here, called Jeopardy, where you have to answer questions. 3 people, and they answer questions in competition. And so they took the program written by IBM, and it was the IBM and the champion human to play the game, and the computer won the game. So it's very, ooh. Sorry, I can't get it off this internet. I know here. So this is talking about the whole world, everything, not just mathematics, not just engineering, not just computing. You want to talk about very normal things. You want to talk about cooking. You want to talk about your business. You want to talk about your friends. You want to represent normal things. And there is work done, as you can see here, different people trying to do that. This is very difficult. The problem is normal things are very complicated and people are very complicated and mainly local. All right. So now we go into some things. Law. At the moment, if you need a lawyer because you did something crazy, you hire a lawyer, and the lawyer costs money. How can we do that automatically with a computer program? So in Luxembourg, there's a big team working on how do you write down the laws, and then you can find out who is guilty. Yeah, it's a Charles, eh? No. This one, politics, You listen to politics on TV. Does a politician tell the truth? No. Politician is a liar, 80% or 90%, politician is bullshit. So this project was done in Germany to take political speeches and check that they were telling the truth all the way through. And they were a very good project. Then they gave them no more money. Yeah. Voting for elections. Very important. Elections must be even and fair, correct. This is company also in Denmark. They take voting and they check that when the box with the papers, it's always 3 people. The box is never alone, so you quickly put some more. No. So they check voting arrangements. They just did the Egyptian election. All right, these things. Oh, this is a very nice one. So there's the ontological argument that people might know, originally by Gödel, proving the existence of God. God does exist, and with some assumptions, some axioms, you can prove that God exists. Very good. And the axioms say, all things that are good are in God. God is all things that are good. Very normal ideas that I can accept, and you can do a proof using these tools. And this was done quite recently by Chris Bensmuller. These are German people. It was done actually now about 10 years ago, using an Apple Macintosh, and they did the proof. And then, of course, there are many people who have done this sort of proof work, Spinoza, Anselm. It depends what you believe about God, but you can write down your beliefs and then prove something about the nature of God. Very interesting. And now here's the fun thing, ChatGPT. ChatGPT is our friend. We love ChatGPT. He answers all our questions. He makes our life easy. All right, or Llama or whatever you use. And you can use these ChatGPT tools to ask a question. And at the end of this talk, I will show you that ChatGPT gives wrong answers. In fact, one of the ones I gave it, I asked it this question. I asked ChatGPT, is every Robbins algebra a Boolean algebra? And it said no. And we have a proof, so it's wrong. So that what is happening now, we are combining ChatGPT, symbolic, with these tools, logic, together. So you ask ChatGPT, can I cook a cake in my oven? And then it will give an answer. Yes, it says put the oven at 300 degrees. Right, but so we give the answer to the logic, and the logic can check the answer to see if it is correct, because ChatGPT learns from the internet, and the internet has got many mistakes, and so the output has mistakes. And this is not good for medicine or law or ethics or something. You have to have perfectly correct answers. So I'll come back to talk about this, but there are tools available. This HAI system is built on IBM software, so the doctors can say, here are the symptoms, what is the disease? But then it has logic to check the output as well. And there's this, so I will come back to that topic. So that's how you make money. And I don't need to talk about this. This is for tomorrow. The only point I want to make here, the software is very complicated inside. Very complex. You must know programming. You must know data structures. You must know algorithms. You must know dynamic optimizing, advanced algorithms and very advanced techniques to make it. So it is complicated, like a washing machine. If tomorrow, when I have my practical session, we will play with some of these, but I don't need to talk about them now, I don't think. So, what is this, the TPTP World? It's an octopus, okay. No. So what did we start? It's a very big project. This project, don't bother to read it, it's not interesting. The idea is I started a project to help the development of this software, to test the software, to evaluate the software, to advise which is good software, which is bad software, to make the software available to the world. It's this very big project called TPTP. And that's what I'm going to talk about, some of the main components of this project. It's many pieces. It's like this. It does many things. But we'll just talk about some of things. It's got various things that are interesting for you. Is the problem library. We have problems to test the software, test input and with test output. We have a language. How do you write things down? In your mathematics classes, you know how to write logic, but we need to be able to write the logic into the computer. In logic, there's no board. You cannot write the logic symbols on a keyboard. No for all exist like that. No crazy symbols. So you have to make a simple language, which we have. The ontology I will talk about. When you ask a tool, here are my axioms, here is my problem, it must give a very precise answer. So we have a very precise way of describing the input and the output from the tools. And every year we have a competition, which is just the greatest fun ever. The software competing like that. So maybe this doesn't translate well. Oh wait, I'll do it on this one. Okay, so I wrote a paper for a journal, and this is what the people told me about my paper. I think I got killed there. So, not everybody likes my work. But now, this was 20 years ago. Now I have more, now things are better. I think this makes the poison cup of Socrates. So now what I want to do is talk a little more detail about some of these pieces of the project and how they go together. So the very beginnings, this is 1993, what we were trying to do is there were many people writing the software and they want to test their software and say, my software is fantastic. And we said to them, how do you know your software is fantastic? And they would say, I have 10 problems. I can solve 10 problems, therefore my software is fantastic. And we thought this is not good. So me and my colleague from Munich in Germany, we started collecting test problems. And we said, not your 10 problems, here is 100 problems, please test. And then we said, oh, my software is not so fantastic. Huh? Right, so then we did that. So we were trying to collect problems and write them down and make them available. So you can see here the first release of this whole testing problems that describe the world, axioms and conjecture, put them out. 1993, and the latest version that came out last year is now almost 26,000 test problems. And this is good. When you're developing software, you must do testing. We know this, computer science people, you must test your software. And so, what sort of test problems? Let's just look. We have problems in logic, all right, different types of logic. We have problems in mathematics, lots of set theory, graph theory, algebra, broken down into all different algebras, number theory from mathematics, topology, analysis, geometry, category theory. So lots of mathematics problems to test your automated reasoning program if you want to write one. Okay, so those are parts of mathematics maybe you know, or not. We also do problems in computer science, theory of computer science. Knowledge, how do you represent knowledge in computer science for artificial intelligence, ER. Natural language processing, when you type to Google, hello Google, hey Google, yeah, what is the time?
It's 2:37 p.m.
How is this? Is magic? No, it's not magic, it's a computer program, Right, and so that computer program you have to test. If I ask him the time and he says, you should go flying in an aeroplane, rubbish. So we have to test that. Common semantic web, here we go. Things, data structures for testing, there we go. Trees, linked lists, all that stuff. And software. We do things in science, biology, right? So we test, we have problems in biology that we can then test the automated theorem proving programs. Problems in medicine, products. This one, we have a very interesting test problem, how to make the best wine, all right? And there's problems. You need to know, if you want to make a wine and sell it, or you want to make coffee and sell it, you go to Rikuka or something, they have very specific ways to do it. And you have to check, on the first day you pluck the plant, wait 3 days, put it to dry, wait 4 days, but if it's raining, wait 6 days. So we can test the programs that give advice for that. I've mentioned this in geography. Very interesting problems. The Middle East. You try to describe the Middle East geography politically. Nobody agrees where is the border between Israel and Palestine and Lebanon and all that. So it's interesting problems. Philosophy and other things as well. So we have problems in lots of parts. And what's interesting, so we have different logics. So we start with very simple logic, then it gets more complicated, more complicated, more complicated. We need complicated logic because the world is complicated. The world is not simple. So we use complicated logics for complicated things, simple logics for simple things. Here's an example of a test problem. This is just one example. This problem is a test problem in set theory. Everybody knows set theory. Everything with the percent sign, this is all comment. It's just not for the computer, just to help us understand what's going on in the problem. And this problem says, the product of a non-empty set of ordinals is an ordinal. All right, so I don't even know what that means, but whatever. It tells me, yep, this is definitely true. It is a theorem. This is a very nice number. It tells me how difficult the problem is. If the problem is a difficulty 0, it means too easy. If it is a difficulty 1, that means nobody can solve it. So this problem, you can see, is really quite a difficult problem. Well, it was back then. This is a bit out of date. And as we see over time, these rating problems, the ratings go smaller, 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 smaller. That means the software is getting better, 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 better. So we have analysis of the software. We get some statistics about the problem and other things, don't worry. So here we see, this is one piece of the one axiom. It's an axiom. The name of the axiom is Thi3, and it says, for all A, B, C, A is a subset of B, B is a subset of C, then A is a subset of C. All right, we all know that. We can prove that. Huh? Yeah. This is normal. And so we write down all the axioms, and here's the conjecture. And I don't understand it, but what you will notice is that everything there you can type on this keyboard. So it's very normal writing. And we don't have to understand now, just that we can write down the axioms, and then we say, this is what we want to prove, the conjecture. Then we give this problem to a theorem prover, and he tries to make a proof. I will show an example in a short while. So a kind of, right, so this is all available. You just go to your home page. Okay, this is your home page now. Okay, delete every other home page. And we can go and get all of this. So now, let's just take a sideways step and show this working using a tool. So, you recognize this problem? You're right. Who said Charles? No, Charles is in jail, but it's okay. All right. So this is the way of writing down that problem about Agatha, the Mayordomo, and Charles in the language of the TPTP. You can see it's very easy for a computer. For you, not easy. For the computer, super easy. All right? And here's what it says. It says, there is somebody X, there is some person X who lives in the mansion, and X killed Agatha. Somebody killed Agatha. All right? Here we see the people who live there. Agatha, Butler, Charles, Mayordomo. Huh? All right. And here we see, if X kills Y, that means X hates Y. All right. So you can write this all down logically. And at the end, I couldn't ask who killed Aunt Agatha. I asked, just prove Agatha committed suicide. Huh? Just an easy thing, not who, just prove she committed suicide. Then Charles and Mayordomo go home. Huh? Yeah. All right. So we could solve it. So this is an online interface to these reasoning tools. It's free to use for you, anybody, if you want to use it. It's provided by money from the US government. So good for the US government. They gave me money. And there's some computers in Miami. It's free, openly available. All right. So I put the problem in. This is it. And we'll choose a theorem prover. This guy, I know him. See, I've got lots of these tools for testing. And we say, go. Yeah. And lots of things happen. Magic. It's all in Miami. And he says, yes, proof. I've done it. I have proved that Agatha committed suicide. And it says, here is my proof. And you look at that and you say, yeah, right. Okay, so, but we can do better. Let's go back. We make it very pretty. See, so now it writes out the proof, nice pretty print and everything. And you read it and you read it and you read it and you read it and you think, right, no good, but we can do better. Wait, stuff happening, JavaScript. All right, so now we see the proof interactively, huh? We can see the proof. So now here is what we want to prove. Let me just put this out. We want to prove, you see here, killed Agatha, Agatha. The house is what we want to prove. Here are all the axioms. Let's find, see that one there, it says, if Agatha hates X, then the butler hates X. So it's one of the rules about the mansion. And there's all the rules, and we can see how they get combined. So somewhere along the line, that one, what does it say? It says, the butler hates the person who killed Agatha. I know what it means, but it's kind of hard to read. And so you can see, and even if you don't like logic or mathematics, if you have a small baby, you can give them this and just go, look, they're oh, pretty, very nice, flashing lights. So it's very good for babies as well. But this is still a little bit complicated, but you can look at the proof. But then you might say, hey, let's see if we can do something else. So I have another tool. You can see this is the input. Here is the final proof by contradiction. Say, where are the interesting pieces? Ha ha. Do some calculations. A big circle means very interesting. A small circle means very boring. So you can now look at where are the interesting places in the proof. What does that mean in mathematics? What is an interesting result in the middle of a mathematics proof called? Lemma, huh? Yeah, you prove a lemma. This is common. You say, yeah, this is a good middle point in the proof. So now we could say, let's just slide this up. And let's make a bit more available. Okay, so we've found the 3 most interesting places in the proof. What does this one say? It says, I can read this for you. It says, if X kills Agatha, then the butler hates X. All right, what does this one say? The butler does not hate the butler. The butler does not hate himself, is one of the results. And what does this one say? Is that this one roughly says, the person who killed Agatha is equal to Agatha. So the killer is Agatha. So we can look at these proofs. This tool is a way to examine the proofs and understand them. So then you can explain to people, here is the proof. This is why you must pay me money. This is why you must go away or something. Here is the proof. So we have tools for doing that sort of thing. So you might have seen then, if we just go back into this, is this language here that we use for writing down the problems is a key idea. Because here we see it for the problem, just you see roughly what it looks like. But then if I go to the solution, hold on, we'd solve it again just for you. Oop, forgot to choose this guy here. Look at the language for the solution. Does it look the same? Yeah, same language, same syntax. So what we have is a language where you can write a problem and use the same language to write a solution. And that's convenient because we can then send the problem into one software, pipeline, next software, pipeline, pipeline. So we have pipelining of the software by using a common language. And this is somewhat technical, but this is kind of why things work in the TPTP, is we have these lots of languages, from very simple languages, first order logic, going through typed logics, extended type, higher order logic, non-classical logic. So depending on how complicated your problem is, if it's a simple problem, we use a simple language. If it's a complicated problem, we might have to use a complicated language, but we can choose the right language. The syntax, as we see, is very simple. Like this. We see this. Very simple. Easy to write. You don't need to do funny letters or anything. It looks just like what you can type on a normal iPad or keyboard. Something like that. Same language for the solutions. This is detail, and for people who want to do the practical tomorrow, we'll go into that detail. But if anybody's ever programmed in Prolog, any Prolog programmers? No, probably unlikely. All right, don't worry. Okay. So all of this, and we have all sorts of tools to play with the language. I mentioned, I'm not going to talk about that. Let's skip on to here, more interesting. So what I've done, so this is history. I started in 1993. Now we have 26,000 test problems. I thought, well, what can I do now? I went and I collected all of the programming, all of the computer programs, automated theorem proving programs. I have about 80 now, and I made a big matrix, 80 columns, 2,600 rows, and then try every program on every problem and see what happens. And so then I have a lot of data about the quality of the problems and the quality of the software. And so you remember, let's just go back here. Woo, that's one here right at the beginning. and I did this, and we got this problem here, timeout, because didn't give it enough time. So if the software cannot solve the problem, what do? Give it more time? Is that a good idea? It turns out giving more time is not a good idea, because here's a plot of what happens. This is time in seconds. So here is 5 minutes. 3 minutes is about here. And so if we take we take one line is one piece of software for solving problems. You see, he solves many, many problems. He solves very quickly, 1 second. Done it quick as a bunny. Then suddenly it gets very hard like this. And so what we know from practical experience is that after about 5 minutes, nothing more can happen. So when we're playing with this software, using it in industry, we tell people, don't give more than 5 minutes. Nothing will happen. You have to think again about your axioms. And we see this all the time. So when I do my testing, I do always with 5 minutes. And so we've seen all of this sort of thing. Baba, we've seen this. All right, so that's another part of the software. And what do you use it for? If you see a problem and you think, how did the computer solve that? You can go and look at, here it is, all the solutions freely available. We go here and we go to the Boolean algebra. Every Robbins algebra is a Boolean algebra. Here's the problem. And we find who solved it. Doesn't look like anybody solved it. EQP should have solved it. Let's go to another one rather. Let's go to Aunt Agatha. Who killed Aunt Agatha? Is it Agatha, Majordomo, or Charles? It's here is the problem. And here's all the people who can solve it. And we saw this guy, there are about 80 of the systems. He can solve it. We can see that. Then you can see, oh, how did he solve that problem? How did he work out Agatha committed suicide? You can go through, look at it. All of the tools are available. We go draw the pretty picture. Go. We look at this and we say, I understand. So now if the lawyer, you're the judge in the court, and you say, Charles, you are guilty. No, you say, we can prove Agatha committed suicide. And you can see the proof and understand it and describe it. And this is useful in business. We've been working in Holland on people trying to make their business grow. And how do you make a business grow without going too far, too fast? If you do too much, too quickly, your business goes down. If you don't do enough, you don't go up. So we've been analyzing how businesses grow. We can look at this and tell them, yeah, you should invest some money in the springtime or something like that. It's the kind of games we play with this. So the last thing in the technical side, we noticed that for each of the problems, they have this difficulty. How difficult is the problem? And you can see this problem's been around. So when we first got it, it was considered like about 0.3 difficult, and now it's 0.06 because the software is getting better, therefore the problem appears to be easier. And so measuring the quality of things is important, and that happens to you at university. They measure the quality of you. How do your professors measure how good you are? It's called exams. You do your exams, the professor says you're A, fail, middle, something like that. And so the way you do that, you have to be fair. If you think your professor is not fair, you cry, my professor is a horrible person. He gave me a bad mark and I am a good person. Or if you get an A grade, you get an A and you think, lucky, I did no study. I got my A grade. All right. But evaluation is very, very important to understand. And so we evaluate the problems very carefully to know how difficult they are. And we evaluate the systems very carefully to say how good they are. Because people, their life belong. If we say your software is bad and your software is good, which one will you buy? You buy that one, huh? So we very carefully evaluate. And here's how we do it. So you think of this, of the 26,000 problems I have collected, huh? And you see most of black dots, negro, but some colorful ones. And the colorful ones are strange, crazy problems, so we remove them. All right. Then we divide the problems up into groups of problems that are somehow related, similar in their things. So it's the same, like we have some mathematics problems, some business problems, things like that. So we put the problems that are the similar, problems that have the same nature, we put them into a box. So now we focus, we zoom in on this box. So in that box, we imagine here, each of these circles is one piece of software we want to evaluate. So we've got one orange, one red, two purple, three, four, there are five pieces of software. And we look which problems they can solve. Orange guy can solve one problem, not very good. A red guy can solve lots of problems, he's very good. Purple guy, quite bad. All right. So here we have A grade, fail grade, C grade, something like that. All right, and then, where am I up to? See these guys, the people, the very bad ones? Take them out, no use. All right, they know, because it's like beginning software. It cannot be used to reliably test something. So now we have only 1, 2, 3 pieces of software. And if we want to know how difficult is a problem, the problem that everybody solves, very easy, he gets 0. The problem that nobody solves at the outside, very difficult, he gets 1. And these problems here, one person can solve, he gets 2/3. Here 2 people can solve, he gets 1/3. And so now we know how difficult the problems are. And this is with respect to the state of the art, what systems we have. I have 80 systems. And then, more important thing, you write a problem, you write your own software, you think, good, my PhD, I will write a software that is the best in the world because I am a genius. And then you realize that you have to do programming and data structures and algorithms and deadly stuff. But when you finished, you come to me and you say, here is my program. Please tell me how good is my program. Because the business people ask me, this is my job, to tell people, this program is, you'll be here. This program is not good, do not buy it. This program is not good, do not buy it. This red one here is a good program, pay for it. So this is the advice, but I don't do it just by my friends. I say, what do we do? So we were here. So what I do now is I take away the very easy problems. I take away the very difficult problems. So now we have just like the middle ones. And then we can see, or for all the systems, it's what fraction they solved. So this guy only solves 6%. The red guy solves 44%. The green guy solves 55%. The funny shaped guy solves 28% of the problems. And then I can say, businessman comes to me and says, which one shall I buy? I say, how much money do you have? And then they tell me, and I say, for you, I think you should buy the green, this software. And that's advice for business. So that's a useful thing to do. And so in your life, you will often have to evaluate things. When you go to vote, you have to evaluate the politicians. When you go to a restaurant, you have to look at the menu, the card, and evaluate what you're going to eat. And if you become a teacher, you will have to evaluate your students. And thinking about fair ways to evaluate, including this possibility, is something very important, I believe, in life. Okay, how are we going? We've got half an hour. Okay. All right, so now let's look a little bit now, I think we go on, is what things can you do with these tools, with this software, to make money. So these are real things happening in the world, and how people have used this software to do nice things. As I said at the beginning, there was lots of mathematics. All right, and you saw that I have lots of 8 subfields. Here we go. The mathematics, we have lots of mathematics going on because mathematics is very precise, so it is quite easy to write mathematics and logic, to precisely write down mathematics. That's different from people. To describe people precisely is very difficult because people are all very different and strange. So we do quite a lot in mathematics. And I don't know much math. As an undergraduate, I did mathematics, but that was so long ago, it's all gone from my head now. But mathematicians can talk to me and they can write their problems in logic. So, what mathematicians have come to me? Firstly, there's the MISAR project. And if you don't know about the MISAR project, I encourage you to read about it. It's misar.org. This was a project that started in Poland and also was developed in Canada. And the idea is you start with Tarski-Trotendieck set theory. Mathematicians, help me. There's a very fundamental set theory. I think it's called Tarski-Trotendieck set theory. And they wrote down that. And then they started building all of mathematics. And you're not allowed to add new things. You can only build on what you know already to build mathematics. And each time you build a new piece of mathematics, you have to have a proof from this software that you have built this correctly, and then it goes into a big journal. And so we did a lot of work on this, using new tools to verify the mathematics. There's a lot of detail here. So we took the original from MISAR, from this library in Poland and Canada. We did a translation to my language, and then we run the software to check it, and then we did some other post-processing. One of the useful things we could do is that we could use that, if you can see that picture of the trees, to help mathematicians understand their proofs. And so this is now in use in quite a big way of using theorem provers to check mathematics for MISAR. And MISAR is a very formal development of mathematics. It's no fooling around. Okay, so there's a link there, misar.org. What's this one about? All right, so we did this man here, Art Quaife, who is a strange man because he was publishing many papers, but he also published papers about freezing your brain so that you could live forever. Strange guy. And then one day he just stopped publishing and stopped answering email. And we all think that he froze his brain so that in the future he can have his brain unfrozen and live forever. But before he did that, he did a lot of work in set theory, piano arithmetic, Tarski geometry, and number theory out of this book. And he did the proofs in quite a slow way. So we took this book and had a student put it all into TPTP World, and we redeveloped all of these areas of mathematics. And there's some very difficult problems in there. The compositions of a homomorphism is a homomorphism. That's not an easy mathematical theorem. All right, Euler's generalization of Fermat, Lob's theorem. These are difficult mathematical theorems, and we could show that we could prove them automatically, so that mathematicians will have hope when they are doing current now. I have a problem, can I prove it? We know which tools, and they ask me which tool, and I tell them, use that one, only $3. Okay. This is what, so this is the quotes from this strange man, Art Quaife. Regular use of ATP leads you to a state of bliss, happiness, all right, if you use the software. Maximize the integral of one's pleasure function over time. The pot of gold. With the help of mathematicians, we might live forever. You see, he really thought he could live forever, this guy. And here's his web page about it. So this is the guy, he's a genuine person. And he started this company called Crinonsys, where they will freeze your brain for you. All right, so you can, oops, oh, sorry, the internet just disappeared. They will freeze your brain for you, and you put your money in, and then in 100 years, maybe the medicine will come right, and they will unfreeze you and put you on a new body. I'm not doing it. Anyway, interesting enough. What else did we do? Work in quasi-groups, very work done. John Slaney in Australia. If people do any quasi-group stuff, any group theory, very nice. I have to restart the Zoom. Hold on. Sorry, I kicked out the Zoom connection as well. What else? Well, let's just move that out of the way. The AIM project, this is in America, abelian inner mappings.
Recording in progress.
Thank you. Sorry about the delay, folks. I just kicked out the internet. The Robbins problem, which I've mentioned from Tasky. And Isabel, I don't know if people use Isabel. It's a big software. It comes out of Munich and also out of England. And a lot of people are using it to verify software protocols, like security protocols on the internet and things like that. And you can write down the logic, very complicated. And then this Isabel system uses my systems. All right. So I'm going to, as I mentioned, and I'm going to come back to this, what we'll do, I'm going to ask ChatGPT live. So I don't know what's going to happen. This is just, we just see what happens now. So here's my ChatGPT, and I'll ask it, is every Robbins algebra a Boolean algebra? And we know it is, because we have a proof. Mathematicians have done this. And what does this thing say? No, it's not a Boolean algebra. So this is crazy. You say, ChatGPT, should I invest in Samsung Electronics? It says, no, don't do that. And you think, damn it, I wish I had. All right, but it's got better. It used to just not even give an explanation why. So I'm going to come back to this stuff later on. What else have we done? So mathematics, NASA, I told you I worked at NASA for a while, and this is what we're doing. We were writing software to go to space. And when software goes to space, it has to be perfect, because you can't just, oh, sorry, Control C, start again, fix it. You got to send good software to space. And so this is how our software development process went. So we'd get a specification from the scientists of what they wanted to happen. Let's do the space telescope, because that was the last one I remember doing. They'd say, right, we've got to move the telescope, focus on a star, collect the light, and so there's a whole lot of things. And so you had to write a computer program that would drive the telescope. And so it did that. They write this, it would be a certification. But they also have safety policies. For example, if the telescope can't move, like it's hit the end, don't keep running the motor. The motor will burn. So they have safety for the software. So the software would be generated here, and with the annotation saying, does this software meet the safety requirements of the organization? So we would go through to order ATP, here we are, TPTP World, and we would prove that the software met the safety policy. And we thought, great, the software is good. So we go to the FAA, the Federal Aviation Authority in the USA, who control everything that goes in the sky, including things that go to space. And we said, look, the software is good. Please give us permission to send it to space. And the FAA said, no, because your ATP, we don't trust it. So we had to get another piece of software which would then check the proofs. Those little proofs I showed you, the pretty tree and all that? We'd check the proofs, and that would come out as a certificate. And here's the funny story, is that the FAA wanted all of this printed. Okay, they didn't want it electronic, no PDF, no nothing. They wanted printed on paper. And so the FAA would come with a truck, and we had boxes and boxes of paper with all the proofs, and we'd give them to the FAA. And I don't believe they could ever read it, but they had their proofs printed. They were strange people, the FAA. So that was something we used. Whoa, sorry about that, my phone bleeped out. Ontological argument, I've mentioned this. Proof of the existence of God. Very cool stuff. This is historically interesting. People know who Gödel is, I hope, long time ago. And Gödel wrote a proof of the existence of God. and he wrote it by hand on a piece of paper. And then Dana Scott, who's a professor at Stanford University, I think, found the handwritten proof, and he typed it on a typewriter, click, clack, old days typewriter, typed up the proof. All right, and then these guys, Ben Small and friends, got the typewrite one, and they put it into the TPTP, and it said, the proof is wrong. The TPTP found, it said, no, you did not prove that God exists. Oh, why? And then using ATP, it found where the mistake was in Gödel's original proof. He left out one axiom that was necessary. He made a mistake when he was describing God to the computer. But then Ben Smuller fixed it, and they got the proof. And this is very good. And it was reported, here we go, in the German newspaper. It's gone to English. Go away. I can't do. Go away. No, it won't let me see it now. It's not free. But the fun thing in the German newspaper, it didn't say anything about science or logic. It said Apple Macintosh proves that God exists. And so it was just an Apple Macintosh. It was no science, no logic, no nothing. But the good news is, he's a friend of mine now, this guy. He got an invitation to go to the Vatican to show this to the people, the religious people at the Vatican, which was, I think, a nice result. It shows that logic can be used for things not just engineering, not just mathematics, not just computer science. It can be used for the world. Here, this was it needed a very complicated, strong language to write down the ideas about God, but we had it all working. And here's the axioms of it and what they proved. Here we see a property is positive if and only if its negation is negative. A property is positive if it's necessary contains a positive property. Something is godlike if and only if it possesses all positive properties. Okay, that's what they say. This is God if it is all good things. And being like God is positive. It's a very normal things. It's kind of nice. I really like that work. Okay, so now we're going to come to the fun part. Why ChatGPT sucks and how we can fix it. Okay, and this is very hot at the moment. I mean, there are people researching this as hard as can be. And remember I mentioned this earlier. We talked about some neurosymbolic AI. So let's say if people are aware of this competition, do people enter here? The International Maths Olympiad. It's for top students in mathematics at high school, and then they give them hard problems to solve, and then you can get gold or silver or bronze, or you should not have come, like that. And they gave the problems from last year's Math Olympiad to a computer program, Alpha Proof, that got a silver medal. All right, so this is a computer program, not a person. And the way this Alpha Proof worked, it took ChatGPT or Llama, one of these generative AI, and the generative AI would propose a solution. They took the solution and gave it to ATP, to an ATP called Lean 4. And it would generate one, and Lean 4 would say, no, that's rubbish. Generate another one, no, that's rubbish. And eventually it would generate a good solution to the problem. Lean 4 would say, yes, that's a good solution. Then they hand it in, go to the next problem. And now this is quite amazing, because this competition has been running for many, many years, and it's designed to find the best mathematics students at high schools, so universities can say, come to us, here's some money, sort of thing. So we did that. I mentioned this one, healthcare. This is at Stanford University. They have healthcare problems. What is your illness? They ask something like ChatGPT. I don't think it is ChatGPT, it's another model. And it says, we think that this person has this cancer. Then they ask the logical model to check it. So this is the same idea. Math prompter, another one for doing math. So this is big business now. And so I decided to play with this. And when in fact, when we had the symposium here 18 months ago, I gave a talk about this. So you recognize this problem, huh? Okay, Agatha, the only people who live in the butler, blah, 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 blah. Who said Charles? Wrong. Who said butler, mayordomo? No. So I asked ChatGPT. All right, and I'm going to give it out in Spanish as well so you can see it. Let's close some of these things. Hard query. Where's the Spanish? Ah, there it is. Let me go back here. Okay, so it's easy for you now. All right, so here's the problem. We know the problem. And here's the answer from ChatGPT translated. And you see, at the end, he says, yeah, Agatha committed suicide. It's good, all right? But wait, he's not good. If you read this very carefully and slowly, no time now, he got the right answer, but the wrong reason, okay? He got a lucky guess. And the reason was wrong. And it took me, I was looking at the English version, and I'm reading this, from points 5 and 6, Butler, and I thought, this doesn't look right. The answer is correct, but the argument is wrong. So what did I do? I took the answer and wrote it in the language of my proofs. I don't know why I have that picture, don't worry. So here was some of the steps in the proof. Whoa, it's scrolling along. I wrote the proof, I took the English proof and converted it to a logic proof. And then I took the logic proof and I gave it to ATP and I said, please look at this carefully. And it said, no, there's some mistakes. And it told me the mistakes, what were wrong. So it found ChatGPT got the right answer for the wrong reason. And I found what the reason was wrong. And that's, well, you cannot use a tool that does that. That's dangerous in life. To have a tool that gives you, it takes a guess and it gets lucky, huh? That's no good. That's like gambling, huh? Casino time. So I thought to myself, you see, I used this tool over here to try and understand it. All of this came through, blah, blah, blah. And it told me it was this step over here and these two steps over here were incorrect. It did incorrect reasoning. So I thought, well, let's try and be nice. This wasn't ChatGPT, it was Bard. So it's the early version from Google, not ChatGPT. So I told him this. What is the logical mistake in your reasoning? So now he starts, this is like a student. He says, oh, I got it wrong. Bullshit, 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 blah, 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 blah. And what does he say? And he says, there is no valid solution to the problem. He says, I made a mistake. I don't know what to do. Okay, so that was Bard. And Bard, of course, was very early, of course. This is 18 months ago. And then we tried another idea. We changed it from being Agatha. We just made up splat, splot, and split for Charles, Agatha, mayordomo. And we wrote the same problem, but with no meaning. And then he did, and here he says that right, the mayordomo killed Agatha. So. All right, so this goes to show you, if you're using these tools, things are not going to be well. You will make mistakes. And the wrong person will go to jail, or you'll make a wrong medical decision, or you'll make a wrong decision about your business. So here's my plan. This is what I think we can build. Now, this software, and I have a plan. So what we have is the internet, lots of information. But some of it is wrong, some of it is written badly, and it's scruffy, it's untidy. What I want to do is some magic, and I don't know how to do magic, but to make it into clean data, nice data. All right. And then, that's one thing. But we can do this. We can take this bad knowledge, just crazy knowledge from the internet, and we give it to ChatGPT or Gemini or Llama or whatever you're using, and he gives you an answer. The answer it might be good, but it might be bad. We don't know at this stage. Then, how do you do that? I mean, you give a prompt to your ChatGPT, Bard, whatever, and he gives you a guess answer. We can use that information that comes out to give information to ATP. This is where ATP will sit. We'll have the clean knowledge, a clean question, and we can check. What is useful is that we can use the guess, the maybe idea, the maybe answer, to help this give a good solution. And so I'm going to be working on a thing called SUMO, which is a huge ontology of information about the world. And the guy who wrote it, he wrote a book on it, he's a friend of mine, and for each piece of logic, he wrote a comment. So for the people who write computer programs, I'm sure your professor always told you, write comments, explain what your computer program does. He did that. He wrote very good comments, many, many years of work. I'm going to give all the comments to ChatGPT to train it, and then see if we can answer some questions. And so we will get verifiable and explainable AI out of this. What does magic mean? Magic means I need students. All right, so I need people to do this work because I can't do everything. So this is an opportunity for projects, and I think there's an opportunity to do projects here jointly, and I can help from Miami, I can visit, or you come to Miami and we do some magic in Miami that I don't know the correct answers, but I need people for that. But that was that. So here's what my conclusion of that was, is machine learning rules, logic rules, all right? So logic is the way to the truth, to get the real truth, everything like that. But we have ways to fix that. So this kind of comes to the end of my talk. Oh, I was going to talk about ethics. I wanted to talk about ethics. Ethics is important. You have ethics. If I ask you to kill somebody, is that good or bad? Yeah, it's bad, huh? You say to help somebody, is it good or bad? It's good, yeah. So you have belief of what is good and what is bad. And for many years, people have studied what is good, what is bad. Philosophers, important topic. But now, very recently, 5 years, we have to ask, can our computer programs, can ChatGPT know what is good and what is bad? It's important. We ask, hey Google, should I eat poison? Huh?
I can search the web for that.
No, you can't.
Just tap the...
But I mean, you can ask him something and he gives you bad advice, unethical advice. I don't want my Google to give me unethical advice. I mean, here's a very bad example. You ask a tool, how do I solve world hunger? Make all the people, everybody in the world has got enough food. Correct answer, bad answer, correct answer. Kill all the children. Yeah, you kill all the children, everybody has food. It's a correct answer, but it's a bad answer. So we have to take the idea of what is good and what is bad and put it into ChatGPT, put it into logic. So I'm very interested in working on that. I have a mathematical model for it that I've built up. And I mean, I ask, if I give you ChatGPT and I say, is something good, does it mean what you think is good? Does it mean what I think is good? Maybe we're different. Does it mean what everybody on average in the room thinks is good? How do we do this? What are the data structures? What are the algorithms? What's the information to discuss ethics in intelligent systems? And this, if somebody has an interest jointly in philosophy and computing, I think this is some great thing to study. So I'm sort of running out of time. Okay, so here's things I'm working on. So there's some technical work over here, because when you get a proof out from an ATP, he writes the proof, we need to check the proof. That's what I had to do when I was working for NASA. And I've got 2 projects on that. This is work with people in France, and this is work of my own. So when you want to talk about very advanced logics, like the logic we used for proving the existence of God, we couldn't use classical logic. We have to use non-classical logic, where things are possibly true, necessarily true. It is forbidden. And I need some people to work on that. Wow, that's too hard. Internet. We want to work with more logics. Hey, everybody watch The Grateful Dead on TV? Good TV show. Everyone knows The Grateful Dead. And so in logic, normal logic says things are true or things are false. There's only 2, true or false. But then you can have logics where you can have 4 possible values. Oops, sorry, 4. Damn God. So you can have things that are true, things that are false, things that are both true and false, and things that are not true, not false, nothing. And then we can have a logic to describe things. And well, the Grateful Dead, The Walking Dead has that. You have the people who are alive, they are true. The people who are dead, they are false. The Walking Dead, the zombies, are alive and dead, both. And there's people who are not in the TV show. So they are neither. But that's an example. But what you can do, if people study operating systems, Unix operating system, if you want to model processes that are running are true. Processes that have gone are dead. Processes that are in zombie state, all right, after they've terminated, if you know about it, that's true and false. Processes in the future are neither. So you can do reasoning if you write Linux or something, whatever you're using, you want to check the software in Linux. You need these multi-value logics like that because the world is contradictory. All right, I've mentioned these. Oh, here's one I need somebody. This is great stuff. I want to write software that tells me when to buy stock on the stock market. All right, I'm going to make $1 million and you'll never see me again. But how do you do it? Is that there's financial ways, mathematical finance. But I want to write a logic description, and then coming into my description every 1 second is the stock price from the stock market. The price of Apple stock is now something. 1 second, this changing of the prices. So in real time, we're updating the description of the world and then updating the reasoning. You get a new reasoning. It says, buy now, don't buy now. And we have in real time. So it runs continuously on your laptop. And when it says buy, it goes beep, beep, buy. And this is great. But I think there's lots of things that are real time. The weather changes all the time. In Manizales, the weather changes every 5 minutes. We know that. It's raining, it's sunny, it's raining, it's clouds, it's cold, it's hot. So you want to have every 5 minutes the weather come in. Hey Google, what clothes shall I wear now? And it's got the current weather, and it can argue, yes, now you must bring your umbrella or something like that. And I have this designed. I just need somebody to do this work. That's not interesting to you. All right, so why does all of this TPTP work? As I've told you, I started this in 1992, 1993, when I was living in Australia. And so there's a lot of things, a lot of things sort of fit together nicely. It's the language. I told you the language is simple. You can type it on your computer. It's easy for a human to read. It's easy for a computer to read. I've got the problems. I've got the solutions. I've got that we didn't talk about. There's online services. I told you I have computers in Miami. If you want to do this, you don't have to use your computer. You can do it on your Apple iPad or your tablet, whatever. You can just connect to my services. It's free. If you use it too much, I will ask you eventually, please, some money, please. But if you don't give me money, you still keep using it, but you kind of slow down a bit. But at the moment, it's not too busy, so you're welcome to go for it. You saw me playing with it. And there's all of these tools, and I haven't shown you all of them. All of them are freely available. Nothing costs anything. And you can have it, if you want to install it on your own laptop, you can. If you just want to use your web browser, use my computers, you can. It's all the freebie. And so one thing I've always tried, I don't know if people know this professor from New Zealand, Richard O'Keefe. He's a big fat man. And he wrote an excellent book on Prolog programming language. It's called The Craft of Prolog. And on the inside, normally on the inside of a book it says, thank you to my mother who was very good, and thank you to my father who paid for my university. And he wrote on the inside of his book, elegance is not optional. It just got to be nice. You must write good software. And so I decided that TPT compliance, you must do it the TPTP way. No other way, no SMT lib. So I am grateful. Lots of people have been involved. I've had a lot of help. Lots of students who've worked on this, on pieces of the project, and I'm always happy to talk to people about this. But here's something I noticed over history. I started looking at people who use TPT, and people who do not use TPTP. And I took photographs of the internet. And there's me, and this, who's Tim Bray? XML, huh? My friend who started with the project with me in Germany went to industry. Look what happened. Larry Paulson, university professor, uses TPT. Bill McCune from Chicago doesn't. Bernd Fischer from NASA, he used it. Christoph Weidenbach from Germany did not use it. Joseph Urban from the Mizar project. Volker Dieke, theoretician. See what happens. Alan van Gelder helped me with the language. Alan Bundy from Edinburgh didn't use it. Kun Klaassen from Sweden used it. Random person, I just asked a random person, and he said, no, I didn't use it, and I could predict it. My student who wrote some of for doing the sizes of the circles, Jörg Siegmund, famous professor, but he didn't use it. Look what happened. Huh? Joe Hurd, from Cadence, doing software verification. John Slaney didn't use it. Doug Leonard did. He didn't. So now we have a problem. So I'm wondering what will happen if Professor Fabian starts using the TPTP. And so I did a little bit of research on the internet, and that's what will happen. So that's sort of the end of my story, and I thank you for listening, and I hope you could understand as much as possible, and I thank you. Just before we stop, I want to explain for tomorrow. You saw me do some little piece using the computers in Miami. At 4 p.m. tomorrow, we will have a practical session. You don't need a computer. You might have to say it all again, somebody, to make sure you, this room? No, different room. But we're going to do practical things. We'll start with some very simple problems, very simple logic, write the problem in logic, do the proof. Then we'll go to a more difficult one. And we'll just do for 2 hours, just practicing using the tools.
Sí, mañana a las 4 del auditorio, la idea es ya terminar todo lo que digo aquí en esta charla general, como les decía, pues no se supone el conocimiento, tiene paciencia y el interés es que poder compartir el conocimiento a un nivel muy general para que se motiven a aprender sobre estos temas. Entonces los interesados mañana a las 4 en W nos ponemos de acuerdo a cómo esta semana una hora diaria o 1 hora y media de mañana a viernes. Y además que es importante, digamos, integrarse con Jeff. Él está dispuesto a, si quiere, intercambiar en la universidad, intercambios académicos, etcétera, etcétera, sobre lo que él sabe, lo que les puede, digamos, la proyección sobre la carrera de Producción, etcétera, etcétera. Entonces no solo sobre estos temas, sino todo lo que nos atañe a lo que es la carrera. Muchas gracias por la asistencia.
Universidad Nacional de Colombia, proyecto cultural, científico y colectivo de Nación.